So we are in unit 9 now. We're talking about some extensions or just applications of trigonometry. And the first one we're going to look at over here is what's called the law of cosines. So in order to sort of understand this a little better, let's first look at the regular Pythagorean theorem, a squared plus b squared equals c squared. In this equation, we know that c squared is the hypotenuse and a squared and b squared are what we call the legs or the not hypotenuse, right? And here, the c squared is opposite the 90-degree angle, the right angle here, which we don't talk about that we know, but of course, we know since it is a right triangle, this measure is 90 degrees. So the side opposite the angle we know went all by itself on the equation here, and the other two sides were on the other side of the equation here, the legs of the triangle, the ones that form that angle over here. As it turns out, the Pythagorean theorem is actually a specific case of a more general law of cosines over here, which states the following. In any triangle, we have this over here. And it looks like it's tough because there's three equations, but it's really not that bad at all. And if we look over here at the last one, c squared equals a squared plus b squared minus 2ab cosine c, this looks really similar to the Pythagorean theorem. So actually, anytime you've used the Pythagorean theorem in the past, you've been using the law of cosines. It's just that with the Pythagorean theorem over here, this angle, the one that's formed by the two sides a and b, right, on this part is 90 degrees. So we would have the cosine of 90, which is 0. So this whole term just was always 0 in a right triangle. If we sort of extend the Pythagorean theorem into this law of cosines, though, we can use it for any triangle. And even though it's written down 3 times here, it's all really all saying the same thing, right? It says the form of it kind of follows the same idea as the Pythagorean theorem here. So if I look at angle A, for instance, if this is the angle I'm dealing with in question, we'll notice then that side A in the equation is all by itself over here. And the two sides that form angle A, side B and side C, are together on this side of the equation. So it looks just like the Pythagorean theorem with this extra term, where we're just multiplying by those two legs of those two sides that form the angle over here, right? As well as the cosine of that angle as well. So why don't we practice with this? It's a lot easier than it seems there. The equation makes it look like it's difficult, but it's just a formula to use. It's just something to plug into. So this says the sides of a triangle are 5, 8, and 12. It says find the angles of the triangle. Honestly, it doesn't matter what we call A, B, or C here. We're going to draw a picture, though, just to get the sort of relative position of stuff together. Because the only thing that really matters, like I was alluding to before, is that we put the side that's opposite the angle we're looking at over here, whether we know that angle or we're trying to find it. We need to make sure that that's all alone on the equation, right? Just the only thing that matters is the relative orientation of these to get the equation set up correctly, right? So if those are the 3 angles, A, B, and C, then this is side A, which is 5. This is side B, which is 8, and this is side C, which is 12. So let's say we wanted to solve for angle B in this, or let's solve for angle C over here. No, actually, let's use angle B just to show us it is really just the same as the Pythagorean theorem with that extra term, right? So since I'm dealing with angle B, I like to mark that one off just as a little mental reminder. And the way the law of cosines works is since I'm dealing with angle B, side B is going to be all alone on that side of the equation. Then I'm just going to take the 2 other sides I have, A and C, and put that on the other side of the equation. It starts out looking just like the Pythagorean theorem, but then we have this minus 2, in this case, A times C times the cosine of B, right? But it's, again, just A times C are the sides that form the angle, and cosine B is the actual angle that we have over here. Now we just plug in what we know. In this case, we had 3 sides, and we were solving for an angle. As we're going to see in the next example, we could always use it if we have 2 sides to find an angle over here. But most generally, if we want to find an angle, I need to know all 3 sides. Because if we look at this equation, there's really 4 sort of variables, quote unquote, 4 things that we can plug into. So we need to know 3 of them. Anyway, we'll just plug in here. 8 squared equals 5 squared plus 12 squared minus 2 times 5 times 12 times the cosine of angle B. And at this point, if we've set up the equation correctly, we're kind of done with the problem solving. It's just taking our time and doing arithmetic. So 8 squared is 64, 25, 144, minus, it's going to be 120, cosine of B. Now it's just a regular like linear trig equation. So I'm just going to combine like terms. The one thing I will stop to point out is right over here is where I notice students make mistakes most often anytime I've tried to teach this. Looking at these here, we know that at this point to solve the equation, we need to combine like terms. Well, like terms are things that are either all numbers or they have the same variables here. What students like to do for some reason is when they see that this number here minus some number times cosine B, they'll sometimes try to do the subtraction right here, which never totally made sense to me, because if I gave you something like 64 equals 169 minus 120x, you would never try to do 169 minus 120 over here, because they're not like terms. Cosine B here, if I don't know what the angle is, it's just like an x. It's some unknown thing. Okay, so I can't combine that with anything unless it also has a cosine B. So the correct thing to do in this case is to subtract the 169, bring it over to the other side. And then we'll get, let's see, we'll use our calculator to help us out. 64 minus 169 is going to be a negative 105 equal to negative 120 cosine of B. Then I'm going to divide by that negative 120 to get the cosine of B all by itself. And I'll have that the cosine of B is equal to the ratio 105 over 120. But we're not interested in what the cosine of B is. We're interested in what the angle B is. So remember from unit 8, then what we do is use the inverse cosine or the arc cosine, whatever you want to talk it, however you want to discuss it there. So we hit on our calculators second cosine to show it that we're using the inverse cosine, and then we just type in the ratio over 120, and we'll get that angle B is equal to about 29 degrees. I'll round it off to 29 degrees there. Okay, and it's really that simple to use. If we want to find all of the angles, that's not going to work. I want to move this all over, but it's not going to work here. If we wanted to find all of the angles of the triangle, well, what we would need to do is use the law of cosines again. We need to use it now for a different angle. So let's go ahead and do that. Let's do this one for angle C, and I'm going to set this one up and sort of jump ahead to the answer just in the interest of time. But if I'm using angle C as the sort of reference angle or the angle to which I'm referring, I don't want to confuse it with terms from last unit here. Well, then I'd set it up so that side C is all on its own on the other side of the equation. So I'd get C squared equals A squared plus B squared minus 2AB cosine of angle C. And once I set this up, the rest we kind of go on autopilot. It's just plugging in, right? So those will be the numbers that we plug in over here. And what was this? I'm sorry, 5 times A times cosine of C. And I'm just going to sort of jump ahead. You can check this in the key. And we would get to a point where we have that cosine C is equal to, let me just double check this, negative 55 over 80. If we did everything correctly here. Right, at which point we would say that angle C is equal to inverse cosine of negative 55 over 80. And just one note here. In the last unit, we said we wouldn't put in the negative when we go to our calculator and hit second inverse, because last unit we were looking for all angles of theta on the unit circle between 0 and 360 that would make that equation true. And because we were looking for all angles, and as we saw with like our ASTC chart, right, there are 2 quadrants for which the cosine could be negative. It could be over here or over here, right? So when we were putting it into the calculator, we didn't put in the negative sign. We used the negative sign to say where we are. And we used the value part to tell us our reference angle. So last unit, we were looking for the reference angle. Here, though, it's a different problem. We're solving something different. So we actually don't care about the reference angle in this case at all. And what our calculators sort of automatically do when they see a negative for the inverse cosine is they put it in quadrant 2, the first quadrant for which there could be a negative, which means it'll give us the correct angle for this one. Long story short, though, for these types of problems, always put in the negative. Okay, so this will be negative 55 over 80. And I get that this angle is 133.4 degrees. Okay. If I didn't put in the negative, I would have gotten the reference angle to go with this one, which would be like 47-ish or something like that, with 46.6 or something. And then I would have had to do what we did last unit to realize that I should be in the second quadrant. So always remember to actually put in the negative sign for these ones here. And then the last part of this is pretty easy. Let's say we're solving for the third angle here, angle A. Well, we don't have to do the law of cosines again. We can use our basic triangle facts. For instance, we know that angle A plus angle B plus angle C should add up to be 180 degrees. It's a triangle. It tells us that, which means that angle C is going to be 180 minus angle B is 29 degrees minus angle C is 133.4, which tells us that, oh, I'm sorry, we're looking for angle A here, not angle C. So that tells us that angle A is going to be 17.6 degrees. And one thing we can always do as a little mental sanity check here is, again, use our triangle facts. We know that the longest side, which is side C here, should be opposite the longest angle. So that checks out. The shortest side should be opposite the shortest angle. So here's the shortest angle, shortest side. That all checks out there. I always like to throw that in just to be like, okay, did I make a mistake somewhere? If I made a small mistake, I'm less likely to get all the results I actually expect. Okay, so let's start out this problem here. This one says solve for all sides of the triangle ABC, where angle A is that, B is this, and C is this over here. Draw a picture. So we have a slightly different starting scenario for this one. We have an angle, and we have two sides over here. And we're trying to solve for the all sides and all angles. With the last problem, it was very clearly we're just going to pick any angle and start there. With this one, though, we'd have to be careful. Like we were saying before, there's 4 things that we can plug into any of this equation, and I need to know 3 of them. So if I was trying to solve for an angle, let's say I was using angle C here, I would need to know side C, side B, and side A, which I don't have yet. So my first thing I have to do whenever I'm given a side angle side setup here is I got to solve for the third side first. So let's do that. Here's side A. That one should be all alone. So I'll set it up as A squared equals B squared plus C squared minus 2BC times the cosine of angle A. Plug in what we know. B is 10.5 squared plus C is 18.0 squared minus 2 times 10.5 times 18.0 times the cosine of 46.5. And then it's just plugging in and evaluating, and eventually we'll get to A squared equals, what do I have for this one? 174.05. Again, I'm just skipping ahead to the answer because it's just arithmetic here, which means that this is 13.2. And obviously, when we take the square root, we know we can get a plus or minus, but this is going to be positive because it's the side of a triangle. One thing I'll point out when you're plugging in here, like don't make it harder than it seems. This is this squared plus this squared. Take your time and plug in each value, because once you get to here, it's not hard. It's just plugging in. And when you see cosine of 46.5, like that's just a number. This whole term here, I can just do 2 times 10.5 times 18 times the cosine of 46.5. And I'm just going to get some number out of it. Okay, so just make sure you plug in there. Then for the rest of this problem, we would have the third side. We can use that to solve for an angle, just like we did up here. And then we can use the triangles relationship over here to solve for the third angle, and we'd have everything. Right, so there's really two ways they can present these problems to us, or we can be presented this problem. We can know all the sides, in which case finding the angles, you just plug in and start. Or we can get side angle side, and we got to find the third side first. Okay, what we're going to learn in our next lesson is the law of sines, and we can use that in conjunction with this to really solve for all sides of the triangle pretty efficiently. So I'm not going to finish this problem. I'll leave that for you. And there's a couple other practice problems as well. You might want to also use any other triangle facts, you know, like with this one here, you notice there's 2 equal sides. It's going to cut down on the work you have to do, as long as we remember some basic facts, like what that means. Okay, but that's all for this lesson. So I will see you for the next one when we talk about the law of sines.